Hello, my name is Emerald Naylor, and today we're going to be going over problem 7-6, parts A and B, out of Elements of Chemical Reaction Engineering. Right at the top, we can see the problem notes right out of the book. And so part A is going to be showing that the steady state concentration of ozone is directly proportional to NO2 and inversely proportional to NO. Then the second part of our problem is going to be part B, and that's just deriving an equation for the concentration of ozone solely in terms of the initial concentration of NO, NO2, O3, and the rate law parameters. So starting out with part A, in the solution, we're going to be using these equations right up at the top. So these are the equations and the reactions involved in ozone formation. So the first part of part A is to take the rate law of the formation of O, and that is right there. So we get the rate laws from basically whatever it takes to form O and then whatever it takes to take it away. So for this first part, we can see that K1 is associated with NO2 to form O, and then we subtract K2 times O2, O, and M, where the concentrations of each, because we're taking O away in that section. So that's how you get the rate law equations for each, and we do that a few more times in the solution. But so once we get the rate law equations for the formation of O, then we set that equal to 0, and that's because of we're applying the PSSH. So when we set it equal to 0, we can get CO and CM equal to this term, and then we're going to save that term for just a second, and then we're going to find the rate law of the formation of O3, which is ozone, and then again we just find the rate law based on the 3 equations that were given, and so then we set it equal to 0 as well as a PSSH, and then we get this equation. So then we sub in this term that we saved right into there, and we solve it out to get the concentration of O3. So then O3 you can see is equal to K1 times CNO2 over K3 CNO. So right there, you can just see that the concentration is directly proportional to the concentration of NO2 and inversely proportional to the concentration of NO. And basically just that means that as the concentration of NO2 increases, the concentration of ozone increases, and then the vice versa. So the concentration of NO increases, then the concentration of ozone decreases. And so that is our final answer for part A. Going into part B, just to refresh, it's to derive an equation for the concentration of ozone. And honestly, a lot of it's around the same steps. So we want to find the appropriate differential equations first. So we find the rate law for NO, which is right there, and then you can see that's equal to that differential equation. And once we find the rate law for NO, then we find the rate law for NO2, which is there, and the rate law for O2, which is right there. So you have all of the differential equations that you need, and differential equations are directly related to the initials of NO, NO2, and CO3. So, also I believe this was, yeah, okay. Anyway, second step would be to apply the PSSH to the rate laws that we actually found in part A. So it's the rate law for the formation of O and the rate law for the formation of O3. So when you apply the PSSH, then once again, you can get the same term that we got previously and plug it right into the equation that we had, and you essentially get the same exact answer, because the initial concentrations of NO and NO2 and NO3 are all related with these differential equations, because within these, when you solve them out, you can explicitly or implicitly get how the initial and final concentrations relate, but that's not needed really for this problem, so you can just get this final answer. And yeah, so if you have any questions, you can drop a comment below, and I really appreciate you listening. Thank you.